Hi everyone, my name's Joanne Kennedy and I'm a naturopath in Sydney, Australia, and I specialise in methylation and histamine intolerance. In this video, I'm going to share with you my knowledge around methylation and the most common things that are going to impact these pathways. So it's not just genetic mutations that we need to think about. We need to think about diet, stress, sleep, chronic gut issues such as SIBO or oxalates, as well as chronic inflammation and hormonal imbalance, as all of these things can put a lot of pressure on the methylation pathways. So here we have the Methylation Pathway Planner by Seeking Health Educational Institute. And I'm going to start up here with methionine. So methionine is an essential amino acid, and this means you need to be consuming it in your diet. And it's the only essential amino acid containing sulfur and is the precursor for these endogenously created amino acids, homocysteine, cysteine, and taurine. Now, the fact that methionine is a sulfur-based amino acid that we get from our diet is a very important point that I'm going to talk about a bit later. So methionine is also the body's major source of methyl groups. We therefore need to ensure we are eating adequate amounts of methionine-rich foods, and animal products provide us with the highest amount of methionine. So we also need to make sure we've got good amounts of hydrochloric acid, as hydrochloric acid activates pepsin in the stomach, which breaks down the protein into the amino acids so that we can absorb the methionine. And then in order for methionine to serve as a methyl donor, it first must be activated by this MAT enzyme. Now, MAT is a very sensitive enzyme and it can be reduced by LPS toxins, which are produced by gram-negative bacteria, interleukin-6 and TNF-alpha, which are inflammation markers, and alcohol is also going to reduce the functioning of this enzyme. So once methionine gets activated by MAT, it converts into S-adenosyl methionine, or SAM, or SAMe, which is known as a supplement. SAMe donates its methyl groups to a whole range of methyltransferase enzymes in the body. And basically, these methyltransferase enzymes need a methyl group to function properly. So some of the major roles of these enzymes are the detoxification of estrogen. They also break down neurotransmitters. They're really important for the production of melatonin, which you need for sleep, as well as energy production. So in fact, 50% of these methyl groups go to making carnitine, which is really important for energy production. And methylation is also important for the biosynthesis of coenzyme Q10, which is also used for energy. Now, methylation is also involved in the synthesis of phosphatidylcholine, and phosphatidylcholine is a major component of our cell membrane. So having healthy cell membranes is really important as they protect the cell and they contain channels that allow important nutrients to enter the cell and then toxic substances to leave the cell. Now, phosphatidylcholine is also a really important component of bile acids. So we need bile acids to digest fat and to absorb our fat-soluble nutrients A, D, E, and K. And last but not least is that methylation breaks down histamine. Okay, so once SAM has donated its methyl group to all of these methyltransferases, it then gets deactivated or demethylated, and it's then converted back into S-adenosyl homocysteine, or SAR, which is then converted back into homocysteine. Now, homocysteine can then be methylated back into methionine with the use of the MTR enzyme, which is zinc dependent, and it also needs methylcobalamin, so that's methyl B12. Now, the MTHFR enzyme down here adds a methyl group to folate, making it methylfolate. And it's this methylfolate that moves up here and binds to methyl B12 that is going to take homocysteine around here to create methionine. Okay, then methionine will then go on to create SAM. SAM will donate all the methyl groups to all the methyltransferases. It will then get deactivated into SAR, and then SAR will form homocysteine, and this cycle will go round and round and round. It will continue round and round and round if you are well, if everything is working properly in your body. Okay, so one of the most things that can block this pathway is having low methylcobalamin or low vitamin B12 levels. So when we think about all the things that can cause low vitamin B12, this makes sense. We can become deficient in vitamin B12 from stress, low hydrochloric acid levels, low zinc levels, taking proton pump inhibitors for reflux, as well as inadequate intake of animal protein. Now, this pathway can also be blocked if you don't have enough methylfolate. Okay, so I'm going to talk about this folate pathway shortly, but essentially issues with this pathway are going to reduce the amount of methylfolate you have. So if you've got low methylfolate along with low methylcobalamin, you're not going to be able to move your homocysteine around to create methionine. And since methylation is so critical for life, the body does have another pathway it can rely on if you're deficient in methylcobalamin or methylfolate. And this is called the short route choline pathway. Okay, so choline is a nutrient. Here's choline. It's a nutrient found in animal protein. And homocysteine can use choline along with this BHMT enzyme, which is zinc dependent, to convert homocysteine through to methionine. So this is an emergency shortcut that the body uses when deficient in methylcobalamin and methyl B12, and it is important because it protects your kidneys and your liver. However, it is this predominant methylation cycle that relies on methylfolate and methyl B12 that you need to support all of your organs, including your skin and your gut and your brain. Okay, so you can't rely on this short route forever. You need to make sure you get your B12 levels right, that the folate pathway is unblocked, and you've got sufficient amounts of methylfolate. Okay, so I will now talk about this folate pathway. So first we need to know that folate, which is found in food, predominantly green vegetables and legumes, is absorbed in the small intestine, and it needs two enzymes to do this. So one is called the brush border carboxypeptidase enzyme, which is zinc dependent, and the other is a soluble enzyme that comes from pancreatic juice and bile. So we need to understand that having SIBO, or small intestinal bacterial overgrowth, can reduce the production of brush border enzymes and therefore reduce the absorption of folate. And having inadequate pancreatic juice and bile can also reduce your folate absorption. So we need to be thinking about this and whether we first need to be correcting folate absorption. So in the intestinal cells, folate gets converted into dihydrofolate and then into tetrahydrofolate, and then it enters the blood in several forms. And one of the forms is 10-formyl tetrahydrofolate, and this is really important for purine synthesis, which makes DNA bases and is involved in gene expression. It also gets converted into 5,10-methyl tetrahydrofolate. Now this will convert into 5-formyl tetrahydrofolate, which is folinic acid, so you might have been supplementing with folinic acid. And as well, it gets converted into 5,10-methyl tetrahydrofolate. So folinic acid is actually really good for people that are sensitive to methylfolate, because sometimes methylfolate can give people anxiety or depression. Now, it's this 5,10-methylene tetrahydrofolate that gets converted into methylfolate with the use of the MTHFR enzyme. Okay, so we also need to talk about folic acid. So folic acid is a synthetic form of folate. It's in a lot of supplements. It's fortified in wheat in a lot of countries. And the problem with folic acid is that it has a higher affinity for this DHFR enzyme than folate from food does. So essentially, folic acid can block the conversion of folate into dihydrofolate and tetrahydrofolate, which will ultimately lead to reduction in methylfolate that you need for methylation. Okay, and the final thing we need to think about in this pathway is the MTHFR gene mutation. So those with MTHFR gene mutation, particularly homozygous C677T, which can cause a 70% reduction in the functioning of this enzyme, may result in low methylfolate in that person. Okay, so coming back to talk about homocysteine again, we can really see how important it is to keep moving around this pathway to create SAM. And when it doesn't, when it starts to build up, it can cause blood clotting. So it's a cardiovascular risk marker, and it can also damage the blood-brain barrier. So the body has another way of reducing homocysteine levels. And this is via this pathway, which is called the CBS or transsulfuration pathway. And to do this, the CBS enzyme, which is B6 dependent, is activated, which will convert homocysteine into cystathione. And then cystathione, using the CTH enzyme, which is also B6 dependent, will convert cystathione into cysteine. So we need to remember that vitamin B6 is really important for this pathway, and it's why you will see a lot of vitamin B6, or there will be vitamin B6 in supplements that are specifically designed to lower homocysteine. Okay, so the body does this to lower homocysteine, but the body also does this to create cysteine. And cysteine is very important as it's needed for the synthesis of glutathione. Okay, so glutathione is the body's major antioxidant. Okay, cysteine also goes on to make taurine, and taurine is really important for making bile acids. It's also an inhibitory neurotransmitter, which means it has a calming effect on the body, and it's also involved in liver detoxification processes. Now, cysteine, we can see here, will also yield pyruvate and sulfite. Now, sulfite then gets converted into sulfate, which is essential for a biochemical process in the body called sulfation. So sulfation is really important. It makes mucin in the gut, which is like a mucus layer that traps and expels unwanted pathogens. It detoxifies hormones, including estrogen and DHEA. It breaks down neurotransmitters, including dopamine and serotonin. It's also involved in drug metabolism through the liver, and it can also break down bile acids. So you can see homocysteine is really important for creating SAM, but it's also a storage molecule for sulfur, so it's extremely important for this pathway as well. So what goes on when homocysteine is low? Okay, so the first thing we need to think about with a patient with low homocysteine is that homocysteine is synthesized in the body from methionine. And I was saying at the beginning, to get methionine, we need to be eating good amounts of animal protein, and we also need to have good amounts of hydrochloric acid and good gut function to actually absorb the methionine. Okay. Also, remember at the beginning, I said that the fact that methionine is a sulfur-containing amino acid is really important, because if you're not eating enough sulfur, then what's going to happen is homocysteine, which is a storage molecule for sulfur, is going to be broken down to provide the body with the sulfur that it needs. Okay, so it's going to be broken down into cysteine, so cysteine can create glutathione and taurine and sulfite. Okay, so the other reason that homocysteine can be low is if you have an increased need for glutathione. So glutathione is the body's major antioxidant. It sequesters all the free radicals that occur with inflammation. So if you have chronic inflammation due to chronic gut issues such as SIBO or oxalates, or you have mold toxicity, heavy metal toxicity, or an inflammatory condition like endometriosis, then your need for glutathione is very high. And in order to make glutathione, your body is going to need cysteine. Okay, so as I was saying, the CBS and CTH enzymes are B6 dependent. So what can happen is if your need for glutathione is really high and these enzymes using B6 are running really fast to chop up cystathionine to create the cysteine, then you're going to be deficient in B6. Okay, and when you're deficient in B6, you can have issues clearing pyrroles from the spleen. You can also have issues clearing glyoxylate from the liver. And if glyoxylate builds up in the liver, it increases oxalate production. And oxalates then go on to create a lot of inflammation in the body and therefore increase your need for glutathione even more. Okay, so this is when we can see people's homocysteine drop to like 4, 3, 3.5. I've seen it that low as 3. Okay, then to make matters even worse, oxalates get into your kidneys. And sulfate and oxalate are bidirectionally exchanged across the membranes. So when oxalates are high, you move sulfate, out into the kidneys, and then it gets excreted in the urine. Okay, so what happens is you start dumping sulfur in the urine. So to get more sulfur, your body will start chopping up homocysteine to create cysteine. Okay, and it will draw down your homocysteine. So homocysteine will start to drop. So sulfate is so important for our body, for our biochemical process of sulfation, that what can also start happening is gut bacteria can start synthesizing sulfur, which is incredible really, but it can make you feel very unwell as you have issues utilizing the sulfur. Okay, so it's sitting there in the body, it's not being utilized. So when you have sulfur-producing bacteria along with this fast-running pathway, this transsulfuration pathway, you can have a lot of symptoms of high sulfur, such as belching, flatulence, nausea, diarrhea, joint pain, body pain, bladder pain, and you will find that you find it very hard to tolerate foods that are high in sulfur. Okay, so we can see having low homocysteine is a really, really big problem that needs to be rectified. Okay, so this pathway over here is called the Biopterin pathway. And essentially the Biopterin pathway is involved in neurotransmitter synthesis. Okay, neurotransmitters are really important for mood. Okay, so we can see here we've got dopamine. So that's really important for feeling motivation. We've got adrenaline and noradrenaline, which we do need for the stress response, and we need serotonin for the baseline of feeling happiness. And here we've got melatonin, which is really important for sleep. Okay, so the functioning of this pathway actually relies on the folate pathway as well as the methionine pathway and the production of SAM. Okay, so we need to come over here and look at BH4. So BH4 is Biopterin, okay, which is made in the body, and it's a cofactor for the conversion of phenylalanine to tyrosine, tyrosine to L-dopa, tryptophan to 5-HTP. Okay, now once Biopterin is used as a cofactor, it gets deoxidized into BH2, which is dihydrobiopterin. Now this dihydrobiopterin then needs to be regenerated back into Biopterin, okay, and it does it via the folate pathway. Okay, it needs activated folates to convert back into dihydrobiopterin. So this is how issues with having low methylfolate or folinic acid can cause issues with mood. Okay, now the other thing we need to look at is we can see that SAM, here's SAM, here's SAM, here's SAM, here's SAM is used a lot in this pathway. Okay, so we need SAMI to break down dopamine. Okay, when dopamine builds up, you can feel really irritable, very anxious. You need SAM to break down noradrenaline and adrenaline. And when adrenaline builds up, you're going to not be able to deal with stress very well. You're also going to feel anxious, irritable. You might also have a lot of problems sleeping. Okay, and we can see that SAM down here actually takes serotonin and it converts it into melatonin for sleep. Okay, so you can actually see how important it is to correct your methylation and to ensure you've got good SAM production to support your neurotransmitter synthesis. Now, the other thing we need to look at on this pathway is that it uses B6. Okay, so 5-HTP gets converted into serotonin with B6, and L-DOPA gets converted into dopamine with B6. Okay, so what happens to B6 if this CBS pathway is running too fast? If your homocysteine's low, you might be using a lot of your B6 to activate this pathway because your need for glutathione or for sulfation is upregulated. Okay, so what can then happen is you don't have enough B6 to make serotonin and to make dopamine, which will really hinder your mood further. Okay, so what I tell all my patients is that we cannot simply be focusing on this MTHFR gene. It's only one enzyme in the body. We need to think about all the different enzymes and all the different nutrients that are required for methylation, as well as issues that are going to cause issues with absorption of these important nutrients, such as SIBO and chronic gut issues, having low hydrochloric acid, low bile acids, low pancreatic enzymes are also going to hinder your absorption of these important nutrients. We need to understand what your homocysteine levels are, because if they're high, it's a very different way of correcting methylation to if they're actually low. Okay, so we need to take an individual approach to methylation. Okay, simply supplementing with these methylated products can often make people worse. We need to ensure we're correcting the person's diet and gut and sleep and stress. We need to balance their hormones along with supporting these pathways to provide the best optimal health for each person.